This is Project 3, video number 1. Project 3 deals with two-slit interference, so let me get a generic diagram for two-slit interference. This will be my screen, and I'll have a mask over here with two slits in it, separation greatly exaggerated in this diagram, illuminated by light of a certain wavelength. I'll call the wavelength lambda, and that's given in the sense that it's provided by the user. I think it takes but prompts the user for 3 inputs: one of the wavelength of the light, and then other stuff. So yeah, that's given. We got straight ahead directions, so there'll be a max there, and it's some other direction. I'm gonna think of this as the first maximum to the right of the central max, because desired fringe separation from the center of the central max to the center of one of the first order maxima. So that represents that. So that could be theta 1. I think we're going to call it theta for now, but I might need to put a subscript 1 on there. And they give us this distance. That is, the user has to supply that. And that's we don't have a standard name for that. I sometimes call that a capital D, but I think I'll avoid that this time, because sometimes people mix that up with the slit separation. I think I want to put that in green anyway. The slit separation, this distance right here, is D. So I sometimes use an uppercase D for this distance, but I might mix that up with the lowercase d for the slit separation. So I'm going to call this just X. It is you don't want to use X for every variable like you do in math, but it really is a distance. So X makes sense for it, and then with that definition for X, it makes sense to call the distance on the screen, which is another quantity that's not a standard quantity in your we don't have a standard symbol for it like on your formula sheet, so you'll find in different problems I use different symbols. I'm going to call that Y. So we're asked to find this slit separation. I guess the idea would be I'll find out what theta is. So theta is equal to, I'll start off, tangent of theta is equal to y over x. So theta is equal to arctangent of y over x. Alright. Then I think I'm in a position already to use m lambda is equal to d sine theta. Then d is just m lambda over sine theta. We want the d for the first order, so m is equal to 1. Theta we just found, and lambda was given. So I'd say we've got it. I guess I'll go ahead and substitute in the m is equal to 1. So in terms of calculations, all I have to do is calculate what lambda is and then use it in this expression. And in terms of the program, let's see, I got to create an outline of this program. So I think program outline. I'll try to number in the steps afterwards, so I don't have to, in case I have to stick any in between. I'll leave a little space too. So input lambda. I got to look at the handout. It takes no arguments for 3 one at a time. Wavelength of the slit, that's lambda. Mask to screen distance, I call that x. And then desired fringe separation, I call that y. In that order. Calculates, prints to the screen but does not return a summary of the values. I gotta output all of those. And the required slit separation. With units and a clear, okay, so I gotta include some words in my output. So input, all those, calculate, I'll call it theta, equals the arctangent of y over x. I think that's what I had up here. Yeah. Calc d equals lambda. I should probably call this lambda. Let's go ahead and change that. Well, I mean written out. That's okay. I think we're okay. I'll go ahead and call it that, and then when I write up the code, I'll know what lambda is. Sine of theta. Now this is interesting. When I calculate that theta, it's going to be in radians if I use the simplest arctangent function. And then here I'll be taking the sine of it, but the sine function assumes that it's in radians, so that should all work out for me. I don't have to worry about getting things in degrees in this one. Sometimes you have to put it in degrees because the directions tell you to, but here we don't have to worry about that. I'll say display lambda comma x comma y and d. So probably up here I can say with prompt. Those are words telling the user what to put in here with, let's say with words or words of explanation, but that conveys the idea. And I think that's it. So I'm going to call that step 1, 2, 3, 4. I think didn't put it in the directions, so I guess you're not required to do it, but I think I'll do a test case. I recommend it anyway, you know, so that you're really doing the program, not just copying mine, and you should always have a test case. So let's have lambda equals 600 nanometers. X equals 3 meters, and Y, let's say we want to have 1 centimeter spacing. Then theta would be arctangent of y over x, which is of 1 centimeter, that's 0.01 meters divided by 3 meters. I think I'll put my calculator in radian mode just so if I have to check intermediate results, I've got that one to check. So I'll go ahead and put my calculator in radian mode and evaluate that. So I get, first off, that's the arctangent of 0.01 meters divided by 3 meters. When I plug that in, I get 0.00 1, 2, 3, 4, 5. I'll copy all 5 of them now. 3, 3, 3, 3, 3 radians. That's good to 3 sig figs. And then I use that in this expression right here. So then D is lambda over sine theta, which is, what I just had to go with, 600 nanometers. Yeah, I'll just put that in as 600 times 10 to the minus 9th. It's obviously 6 times 10 to the minus 7th, but I feel like writing it that way. Meters, oops, minus, that's a big difference. Yeah, I think I'll make a little more room for that minus sign. Minus 9 meters, and then divided by the sine of 0.0333333 radians. So D is equal to sine, nope, 600 times 10 to the minus 9th meters divided by the sine of 0.03333 radians. And when I plug those in, I get 1.8. 0, a few more zeros, times 10 to the minus 4th meters, which is 0.180 millimeters, which is doable. Okay, so that would be a value that I can use to check to see if my code is working. Alright, that does it for the pencil and paper part for project number 3.